All right, welcome everyone. Thank you for coming out here. I realize I'm standing between you and lunch, so it's going to hopefully we'll try to make it exciting and fun, and we'll have a good time over the next few hours. The next hour we'll shift gears a bit compared to the presentations from earlier this morning, where it was deep down in the JVM. This is a bit of a higher level presentation with hopefully some interesting ideas for you to take home, or some new ways to look at things, or to approach maybe how you look at your system. So the next hour is going to be a presentation about immutable infrastructure. We'll dive into the details of what that means in just a second. A few words about myself. So my name's Axel Fontaine. I'm originally from Belgium. I've been living in Germany for the last 10 years. Did many years of consultancy and did a bunch of things, lots of presentations in the different technical conferences in Europe on continuous delivery, and these days also what I'm doing here today with immutable infrastructure in the cloud. I'm also the creator of an open source project called Flyway for database migration, so evolving a schema of a relational database over time. Just out of curiosity, who's heard of Flyway before? So that's about 3/4 of you. Who's using it in production? Very good, about a third. Excellent. These days, I'm also the founder and CEO of a company called BoxFuse. What we do is deployment of JVM, Node, and Go-based applications on AWS. And the presentation today is a lot of the lessons learned from the last 2 years that we've been doing this. What are the implications of this model? How does it affect applications? How does it affect everything around it? So it's a little bit of our lessons learned, both from ourselves and our customers using our product. So you'll see we'll have a very busy agenda. In 60 minutes, I think I've got 95 slides, so it's going to be pretty rock and roll. I'll do my best to keep you awake and entertained. So if you have any questions, I would like to ask you to hold on to them till the end. I'm around the whole day. We'll have another small session at 6 this evening during the break as well, about further details about this as well. But feel free to catch me at any time, also in the hallway and all that. I'm always happy to chat about anything you like. So just hold on to them to the end, and then whoever wants to rush off to lunch can just do that, and we're not holding them back. So let's get started. And we're gonna start by taking a big time travel machine, and we're gonna travel back to the wild times of the 20th century. So we had these guys running around. That was pretty exciting. This was how we used to play music, and that would be how we would be rewinding it. So it was pretty exciting indeed. And we had this guy, and he loved it when a plan came together. So when his plan was to get a server, this is how he would do it. He would get on the phone, the old style with the cords, and he would call his good friend Michael and say, "Hey Michael, I would love to get a server." And Michael says, "Well, sure." And then eventually, a few weeks later, he would receive a pizza box in the mail, and then screw it in the rack and connect the network, the power, and then what? Still doesn't work. So he gets back on the phone and calls a young criminal from the western coast of the United States that then delivers him some criminal software, which then gets installed onto that and patched, and off we go. So if you look at this picture here, we really have 3 main components. We've got the data center, we've got the hardware, we've got the software, and all that together is really the classic on-prem model. So just out of curiosity, who's running all that themselves in their company? Who's fully on-prem? Who's got their machines in their own basement somewhere in the company, or own the data center? Just 1, 2, 3, 4? Okay, very good. I expected more. What we have, if you do have that model, is that you have quite a number of challenges to master. It starts with things like ensuring you have reliable power, that you have backup generators in case the main power falls out, or that you have reliable redundant networking, that you've got good airflow for cooling, that you've got things like physical security of the building in place, or also things like enough physical space, because it's not enough just to have enough space for your current set of systems. If 2 years from now you want to upgrade your storage, you can't just unplug everything from your production system, wheel it out, wheel the new storage in, and plug it in again. You need enough space for a transition period. So all these are things that we need to think of. And once we've covered all those, then we get to the whole relationship with Michael, where we must plan a long time in advance and nurture that relationship, make sure we've got the financing covered a long time in advance. And once we've got all that, then we're ready to move to the software side of things, where we can then finally start installing an operating system and patching it and installing our application and updating it. So it's really a whole lot of things that we must master for this model to be successful. And if you look at it, there is actually quite a lot of those that are quite far removed from the actual problem we're trying to solve for our customers. If we're trying to solve a business problem for our customers, learning how to best run diesel-powered generators is quite far removed from that. So a number of people said, well, you know what, all nice and well, but you guys are really good at data centers, and God invented this wonderful thing called the credit card, so why can't we come together? And we'll come to you, and well, give us our credit card. We'll give you our credit card, and you guys take care of the data center. We'll come with our own hardware, and we'll plug it in the rack. We'll have a 1, 2 for you unit. You just supply us with reliable power networking and so on. And this is the classic co-location model. Now, just out of curiosity, who's doing that these days with their company? So you don't own the data center, but you own the servers, and you have them in somebody else's data center. Just 1? 2, 3, 4? More and more. Okay. At some point, of course, somebody said, well, you know what, that whole relationship with Michael and having to deal with it and ordering things a long time in advance, you don't really want to be dealing with that either. So let's again use a credit card for that. And why don't you guys take care of the hardware, and I'll just come with the software. You deliver me an x86 64-bit machine with this amount of RAM and this type of CPU and disk, and then we'll be happy, and I'll just pay you some monthly amount with my credit card. So this is the typical model of OVH or Hetzner, where for about 50 euros a month you get an i7 with 64 gigs of RAM and a terabyte of SSD space. So this is the classic root server. Now, if we bring this all back to software, let's get to know each other a little bit. So I would like you all to raise your hand and keep it up as long as what is up here applies to you. So are you currently on a project with an automated build? It's just making sure everybody's awake. Huh? We've got all the hands up. Yes, yes? You don't? Okay, fair enough. So one guy doesn't, but all good. Who's got unit tests on their project? All the hands still up, some hands down on the back, but okay. Who's doing continuous integration? Very good, still pretty much everyone. Acceptance tests in the like Selenium or WebDriver, the kind of black box system tests, we're at about 50% maybe. Who's doing continuous deployment of code? You push and it goes live into production. We've got about 30-40%. Who also does the same for database changes, configuration changes? We've got about maybe 10% of the hands left. And who's doing fully automated infrastructure deployments? We've got just one in the front. Hey, applause. Good job. All right. If we look at that workflow, if we've got our version control system up there, once we commit and push something to our version control system, we actually want to make sure that we don't introduce any kind of errors in there. Errors like things that we have forgotten to check in, or things that have certain dependencies on our local machine. And that's why we have the CI server. Some kind of neutral referee that will then pull down the latest version of the sources whenever they change, and will run a build and test them and produce some kind of artifact. And the artifact we produce there has got a number of qualities that we've learned to appreciate over the years. When we produce in the JVM, for example, a jar, a WAR file, an EAR file, but this could be an RPM, this could be a zip, this could be anything, we produce one immutable unit. It is really something that we don't really go and patch after the fact, or we don't extract it, change some files, and zip it up again. Instead, whenever there is some change, we just go back, we commit the change, and then the build kind of runs again, and we regenerate a new artifact. And we promote that same artifact unchanged from environment to environment. Why do we do that? To avoid the classic mistake of building a separate artifact per environment. Why is that a problem? Because you then end up with a different artifact in production than the one you tested in test. So we don't want that. Now, if you look at all the layers from our stack, if we start from the hardware at the bottom, on top of that, we usually have some operating system kernel, and then we'll have some libraries, and then we've got some language runtime, in our case, the JVM, and then on top of that, we've got an app server embedded or not in our application itself. So this is a pretty classic stack, and if you look at the whole CI story we just talked about, it's really just talking about these top two layers. And the question is why? Why only these top two layers? Or what is fundamentally different about those layers than the layers below it? Or is there something different at all about those bits and bytes? Maybe, maybe not. So if we keep our little picture in mind here, and we've produced our artifact, and we want to get it out to some kind of server out there. If we've got our target machine here, we push our artifact to some artifact repository, and then we pull it down from the artifact repository, we stop the old version of the app, we start a new one, done. Actually not too bad when you look at it this way. Except, of course, that the world rarely looks like this. It looks more like this, where you have many machines in many different environments. And of course, any kind of difference that you introduce at any layer on those machines is a potential source of trouble. And you have to make sure that they stay as identical as possible to avoid any late surprises there. So the world doesn't just stay in place, of course, so at some point, all of these will need updating on all layers, on all machines. So whose job is that? That's the system administrator. It's the system administrator's job to make sure that all the machines are up to date, that they're aligned, that everything's working well. Now let's travel a little bit further back in time, about 100 years ago. And we had this gentleman in the automobile industry, and he had this famous quote. If I'd asked my customers what they wanted, they would have said a faster horse. And guess what? This is exactly what we got in IT. Instead of the system administrator, we now have the automated system administrator, better known as the chefs or puppets of this world, where you perform the same basic task as the system administrator, and where you align different systems based on some templates or recipes. It's just a little bit faster, a little bit less error-prone, a little bit more efficient, but the basic task is the same. Now let's fast forward back to the present day. This is a quote. It's almost 2 years old now, so it's certainly evolved a lot since then. But this was a quote at AWS reInvent in Las Vegas, a big yearly conference, 2 years ago. Every day, AWS adds enough server capacity to power the whole $7 billion enterprise. Amazon.com was in 2004, weekends included. So you really have to let it sink in to realize the magnitude of it. That's yesterday, that's today, that's tomorrow, that's the day after, and again, and again, and again. It's just incredible. We have never experienced this before. We have really shifted from a world of scarcity where we had to really carefully look how we were utilizing every machine that we have to a world of abundance where you have virtually limitless supply of resources when you need them. The other big change that the cloud brings to the table is a clear separation between the control plane and the data plane. In this example here, control plane, we've got a nuclear power plant. The control plane would be the control room where you've got all the dials and the monitors, and the data plane would be the chamber where here you've got the pool with the submerged rods where the reactions are actually happening. If we bring that back to software, the control plane could be your console, for example, for your cloud, and the data plane would be your actual instances doing work. The new thing now, of course, is that the control plane can be fully driven by machines. You've got APIs to provision any kind of resource that you want. And the new thing, and something that's never been possible before, and certainly not on any kind of so-called private clouds, is that you can shut it down and stop paying for it. If you have a billing system that needs to run for 5 hours a month, you start it at the beginning of the month, you let it run for 5 hours, you shut it down, and you stop paying for it until the next month. And this, for me, is going to be something that's going to be hugely interesting in the next few years, where we're going to see, I think, a clear convergence between business and architecture, where we're going to be integrating cost as a major driving force into how we're going to design our systems and how we're going to make sure we can optimize to make them as economical as possible. I think this is really, it's early days, but I think it's going to be very, very interesting what we've got ahead here. And so in light of that new reality, I strongly believe it is time to rethink the faster horse. If we start by assuming that what we have at the bottom there is just undifferentiated heavy lifting, it doesn't matter, then we can replace the physical hardware by virtual hardware. And all of a sudden we have a bunch of new possibilities. Instead of just producing regular artifacts, we can start producing images of entire machines, which we can then just push to some artifact repository and pull down all at once on the virtual hardware, so that we go from a world like this to a world like that. And if you design your machine images properly, you can even make them run on multiple kinds of virtual hardware just fine. The whole issue that we had with updates on individual layers, on individual machines, disappears, because that's all been baked in as part of the build process, so that you can then have the same machine image that you can promote unchanged from environment to environment. But of course, there is one big problem left, is that the size of our machine images and the size of our network pipes don't really fit together. We've got a bit of an issue here. It is complicated to push machine images multiple times a day over the internet. It is expensive to archive thousands of versions of them per year. So how can we deal with that? Well, let's turn to some wisdom. This is a quote. I forgot who I've got it from, but it's a very good one. Running servers in production should be like going backpacking. You take the bare minimum with you. Anything else is going to hurt. Now, this is a picture I took about two summers ago. We're at the bottom of a mountain in Bavaria. We're ready, like a Saturday morning, 10 o'clock, ready to go and hike up the mountain, about 1,000 meters vertical. So it's a good hike for the day. And then we've got these 4 guys coming down. And so we start chatting to them. And so they'd gone up the mountain the night before with a 20-liter wooden barrel of beer and the 4 big glasses and a hammer. And so they drank it all at the top of the mountain with the 4 of them, and they were just on their way back down there. So when you think about it, it is the most inefficient way possible to get up that mountain. And yet, when you look at how we run our production machines, where we've got a 20 megabyte application and gigabytes of stuff around it, it just doesn't make sense. So if we're going to be trimming some of that fat, we should decide by which criteria to go by. And I strongly believe that in the software world, we are really there as an enabler for the business to make new things possible, or existing things more efficient, or being able to optimize that. So this is really something where we should then ask the question, from everything we've got into that machine, what is actually adding business value versus what is just technical ceremony? So let's have a look. If we've got our machine image here, we're going to X-ray into it. We've got a bunch of components. In reality, there's more, but just I've put a few up here. And let's go down the list. Start at the top left and see what we've got. So if we've got our application there, we're going to keep that, because that's actually solving the problem, so we need that. But if we're in a virtualized environment in the cloud, do we need support for old binary formats, 32-bit CPU architectures? No, we don't. So we're going to get rid of that. We're going to keep the app server, because we will need that to run our app. But has a customer ever benefited from the fact that we had some man pages installed on those machines? No, so off they go. Has a customer ever been excited about the fact we could run apt-get or RPM on our production service? No, goodbye package manager. We're going to keep the language runtime because we need that to run our applications. But if our application is written in Java, do I need a C compiler installed on that machine? No, I don't. It's not 2006 anymore, so the days of having 5 different windows open with tail-f expressions and watching the log file scroll by is really a thing of the past. We've got great solutions with centralized log servers that are very mature, that have been available for a long time, so log files do not belong on individual machines. If I don't have my log files on there, do I need things like VI and all those other editors? No, I don't. All these other random utilities that are installed on those machines by default, do I really need them for my application? No, let's get rid of them. If I don't have any of that, do I even need to log in? What for? Goodbye SSH. If I can't log into those machines, do I need multiple users? No. If the very things I set out to protect simply aren't there anymore, do I still need a firewall? No. Do I need multiple shells? No. Do I need drivers for tens of thousands of pieces of hardware when all I need to support are 3 or 4 virtual interfaces? No. We're going to keep some libraries because we'll need those for our language runtime. We can dispose of many random daemons, and we're going to keep the OS kernel to actually drive the hardware. And what we have here is the bare minimum, which is actually adding business value. And if we fuse all of that together, we get what we call a bootable app. And this is a very different world. For Go-based applications, for example, this is about 7 megs plus the size of your app. If you're on Node.js, it's about 15. On Java 8, it's about 40 megs plus the size of your app, and that already includes the JVM, the kernel, any other bits that you need. And all of a sudden, the difference is quite big compared to the machine images that we had before. It's not that much of an issue to push that over the network multiple times a day. It's not that expensive to archive thousands of versions per that per year. So this is actually quite an interesting model. But I know a number of you are thinking right now about a bunch of scenarios where this would never work. But it doesn't matter, just use it for everything else. Because as much as we would all like to go back to the office on Monday and think that we're working on the next Facebook, on the next Twitter, on the next big thing, we actually look at the projects we're working on, and it turns out we're hardly pushing the boundaries of technology. We may be solving interesting business problems, but we're not really pushing technology to the edge. Instead, we just want to get the job done. And so the perfect modern cloud-native microservice is a very, very good fit for a model like this, a standard problem with an industrialized solution. So we're going to see it live. I'm going to show you to show you that it's real. It's not just hot air. And we're going to have a bit of a look at this. I've got a small Spring Boot application here ready. And we're going to see how that could work. So we're going to use my company's tool for that. We're going to use BoxView. So I'm just going to switch over. I've got just the main class of a Spring Boot application. Just changed it here. Add some exclamation marks, hide jetconf. And we're just going to build this guy. So I've got our Maven window here. Just going to quickly build a project. Just clean package. Should take about a second. Let's go. Let's go. Here we go. I think the screen recording software may be slowing things down a bit on the hard disk. Okay, so we've built this now, and what we're going to do now is we're going to create a machine image from that, and we're going to run an instance of it on the VirtualBox. So the first thing that we do now is BoxViews run, and what's happening now is that we have some, let's see. Okay, so we've discovered that that we're in a Maven project structure. We looked in the target directory. We found that we had a jar file that existed there. We've discovered that it was of type Spring Boot. We've created an image for it, and we are now launching an instance of that image on VirtualBox. So we also discovered that we needed one port for that, and we forwarded that port. So this is just booting. This seems a bit slow. I think it's the screen recording software which is slowing my machine. So sorry about that, guys. But let's go back up a bit. Okay. So here we go. So we fuse the image. Normally it's about 3 seconds without the screen recording software. The total size of the machine is about 56 megs for everything included in the JVM. We had our one port here that we discovered. We mapped it onto a port on localhost, and then we launched an instance of it where we're basically here we're booting, and we're displaying a bit of a summary of what we've got on board. And here it's our JVM booting and our Spring Boot application up and running. So this is our URL. Let's copy paste this guy and go to a browser, open a new tab, paste it, and here we go. That's our brand new machine image that we've got up and running that we created like a minute ago. So so what do we have? If we have a look, we're going to see. So let's see what we have in terms of images here. We've got one image that we created just now. This is the size, this is the port, Java 8.102, and based on that jar, and what have we got running? We have one VM running at that URL that we launched just now based on the image that we created with 2 CPUs and a gig of RAM, configurable of course, but those are the defaults. So what we can do now is take the same image, unchanged, and push it out to AWS. So just going to take the ID of the image here and switch the environment to production. So we're not regenerating any kind of image. At this point, we're just taking the existing image and we're pushing it out. So this is a test for the Wi-Fi. So let's see. So please don't download anything on your phones right now. But it seems to be going smoothly. So we're pushing out our image, in this case to AWS in Frankfurt. So we're verifying it gets encrypted and signed before. We're verifying the signature, decrypting it on the other end, and now we're basically waiting for AWS to convert that image to a so-called Amazon machine image, an AMI, which is their machine image format from which we can then launch some instances. So this usually takes between 30 and 50 seconds. So let's see how long they need today. So the thing is here. So when we created that first image, we really created 2 things. We created the disk image and a descriptor. And the disk image has been unchanged on VirtualBox and here on AWS, and the descriptor has been translated locally to something VirtualBox understands, and in this case here, into something Amazon understands for the AMI. So our AMI was created in about 22 seconds. We created a new security group and an elastic IP address. That's a virtual IP address that we can remap. We created a new domain name, mapped it to our new IP address, created a new instance that we started, and we basically waited for an HTTP 200, got that, and reassociated our domain name and our elastic IP address with the new instance that we launched. So just copy paste all that, and gonna open a new tab. Here we go. And that's basically our same image, like identical to what we had on VirtualBox, down to the last bit and byte, now running on AWS. So what we can do, of course, is we can modify this now. We could say, jetconf, here we go again, save this, and just quickly gonna run a build again. So let's see, should take another few seconds. Here we go. And I would say let's go straight to AWS with this one. So I'm just going to do box use run environment production. So basically what we're going to see is that the version number didn't change, but the checksum changed. So we allocated a new version number for a new image that we're now creating. So again, should take a few seconds. I think without the screen recording software should be about 3 seconds on this machine. And we're pushing it out again to AWS. So this is, again, just here over the Wi-Fi, just the full machine that we had all the way from a bootloader, the kernel, and all that to our application out there. Let's see, and we're going to convert it into an AMI as well. So what really happened when we created the disk image was that we looked at it. So we found a jar from a Spring Boot application, and we know, okay, a jar depends on the JVM depends on the C library depends on the Linux kernel depends on the bootloader. So we basically created an operating system from scratch with exactly those pieces. So it's not based on any kind of existing distribution or anything. It only contains literally what we need. So we created an empty disk image, put those pieces in, and then started it. So let's see. So we're now waiting again for a new AMI, in addition to the one that we had before, to be created for the new version of our software. So we just got the AMI. We're now launching a second instance. So if we see the old one is still, where do I have? I have some green thing. Let's see. Okay, so the old one is still up and running. And in the meantime, so we're launching a new one. So we're basically, because we don't live in a world of scarcity, we're in the world of abundance now. We can just start additional resources for short periods of time, and that's fine. So it's still the old one running. And we're now basically for the instance, waiting for the instance to come up. So this is basically every second we're kind of checking for an HTTP 200, make sure our application is up and running. And we just got that, so now we're transitioning the Elastic IP address from the old one to the new one. So it's still the old one running at the domain, still the old one. And here we go, we've got the new application or the new version, the new image there up and running, and we're now terminating the old instances and contracting our infrastructure footprint again. So this is probably a little bit different from how most of you would deploy your software today. And this is not without implications. If you do go for a model like this, there are a number of things that change. The first one is that there is a strong shift in focus, where before the individual instance used to be really the center point, where that is something where you would focus on. These days it is so much more about the service. The service should be available with sufficient capacity, with sufficient performance. Which individual instance is actually fulfilling the request doesn't matter as much anymore. In a sense, individual instances become disposable. So that we really get to the point where we can get to what the famous saying says. We can start treating our servers like cattle instead of pets. So instead of just giving them a nice name and making them just perfect and really nurturing them, we now get to a world of anonymized mass production. Give me another 10 of the same. They should be identical. There's no emotional attachment to them. And that's actually a good thing, because of course the hard reality is that once you don't need those servers anymore, this is how they end up. So it is a bit brutal, but that's perfectly fine. It's a very good thing that we're able to do that. Because effectively, we are eliminating CRUD for servers. We are getting rid of the U. We're still creating them. We're still accessing them, we're still disposing them. We are not updating them in place anymore. And that's actually a good thing, because we come from an industry where we used to pride ourselves of, look, I've got this Linux machine and I haven't rebooted it in 3 years. It's fantastic. And well, the problem is that the longer a machine like that stays up, the harder it is to recreate exactly. If you need a second one, just the same, or if this one, for whatever reason, dies and you need to rebuild it. And the bad news is that it will fail eventually. Whether it's due to hardware or to software, you will reach a point where you will need to do that. So all those very long uptimes we used to be so proud of may not be the best of ideas after all. So, if my stuff comes and goes, like in the demo, for example, first we were accessing the first instance, and then we were accessing the second one, and the first one was getting terminated. How does service A know how to talk to service B? The classic problem being addressed by service discovery. There is a lot of activity in this space. If you think right now from good old zookeepers to console and Eureka, and there's a lot of activity in the tooling space there. But in my opinion, I feel that a lot of this is just too complicated for the problem we're trying to solve. A lot of them were designed for a different era also, whether they were designed for on-prem or in the case of Eureka, they were designed for AWS pre-private load balancers. You could only have public-facing load balancers, and that's why Netflix had to go through the effort to design something like that. But now we do have other possibilities. So I think there's a simpler way. So let's have a look. If we've got our instances, our current understanding, our assumed agreed definition of the service boundary, if you have some kind of service, is that you would have some kind of private persistence where you wouldn't really do database-based integration anymore. Instead, all that would be just part of one service so that you can have nice validation. You're more free to evolve the structure of your data or whatever you use there without having too many external dependencies on it. And so all we actually need to do is extend this slightly. If we add a stable entry point with an internal registry, we can actually solve a whole bunch of things. In our little demo there, the stable entry point was the elastic IP address and the domain name associated with it. And the internal registry of the elastic IP address is keeping track of which actual instance it is presently associated with. In the beginning of the demo, it was associated with the first instance, and then later with the second one. As a client to that, me with my browser, I didn't have to care. All I had to care about was remembering the elastic IP address or the domain name. If you have more than one instance, you can use something like an elastic load balancer that forwards then the request to whatever instances are running in the backend there. So whether it's currently these 3, or if 10 minutes from now it's 5 different ones, as a client to that service, not your problem. All you need to remember is the address of the load balancer. And the load balancer keeps track of which instances are currently healthy and ready to serve traffic. You don't need to worry about any of that. You don't need to bring any of that complexity into your application code. All you need to remember is one address, and you're done. Not your problem, what is running behind it. The nice thing about a model like this is that if this becomes your basic building block, it becomes much easier to reason about your overall architecture, because these become like Lego bricks that you can start assembling and clicking together, and you have a very simple interface to the outside world. And that's actually very, very powerful. Now, let's talk a bit about security, because that's another big aspect. You could almost rephrase the question as when was the last time your toaster got hacked? I think when you think about it, all things being equal, the more moving parts you have, the higher the likelihood that one of them will break. I strongly believe that complexity is the enemy of security. And so what we've done here is we've really reduced the potential attack surface to the absolute minimum possible. The other thing that's interesting, of course, is that by shortening the lifetimes of those instances, it becomes much, much harder to actually do something useful with them if you manage to Troyanize them. If somebody had Troyanized that first instance, whatever Trojan would have been planted there would have already died 3 minutes later with by the time it would have disposed the instance itself. So this becomes much, much harder to really stay inside if you do get in. And of course, if you do get in, what are you going to do? When you think about it, in a classic, in a classic Linux distribution, you basically provide an attacker with all the tools pre-installed that he needs to further penetrate the network. It's insane. All the utilities are just there for him to use. They're not there anymore now. So you get in, and what do? You can't do anything. So this is really quite interesting. Now, configuration is another aspect of that, because you may say, well, you know what, Axel, so nice and well, we've got our same image everywhere, but I don't want to access my development database from production and vice versa. I want nicely orthogonal environments. I want to make sure that works well. So how can we deal with that? The first thing is to recognize that from our configuration, there's a whole bunch of things that aren't really that interesting. We've got many properties that aren't sensitive. They aren't really relevant. They're only something that's useful to our application. So a lot of these you can just directly bake into your application for all environments. And you just select at runtime which set to use via a simple technique called environment detection, just the simplest possible way to find out in which environment you are by either auto-detecting IP ranges or simply passing a parameter that says, well, your environment is such and such. So how do you do that? How do you pass a parameter? Well, every cloud provider out there today offers the possibility at instant startup to pass in arbitrary data. In the case of AWS, this is called the user data, and you can do with it anything you want. So what you can do is, for example, pass a shell script that exports a number of environment variables. And those environment variables could be your password is such and such, or the URL of your database is such and such, or your environment is staging. Load the properties for staging. This is something that you can do there as you want. I think aim for the simplest thing possible and move up from there. And if that's not enough, of course, this doesn't prevent you from moving to things like using configuration servers and so on. These are just techniques to start with the simplest model possible. Now, state is another interesting one, of course, because if we are going to be getting rid of entire instances, whatever persistent state was living exclusively on those instances will die together with them. So you have to make sure that persistent state doesn't live exclusively on any of those instances. So how can you do it? You can keep it external by accessing specific database servers or storage servers just out of the instance. They've got very different concerns they need to deal with anyway, because that needs to be replicated and you need to make sure that works well. So just keep it out. You can either build your own, or you've got great hosted services available today. Whether you're on Google, on Azure, on Amazon, you've got fantastic hosted services for any kind of storage. We personally have been using Amazon RDS for Postgres since years, and it's fantastic. You just stick a box, and your database is then deployed in a geographically redundant, highly available fashion. You've got point-in-time backups available to you, so you can restore exactly at yesterday, 11:30 at night. Bam, give me that exactly. Very, very useful stuff, and very, very easy to work with. If you're using a database, a relational database, think about the schema that will have to evolve at some point. So try to do it on application startup so that the application always stays in sync with the database, or the database always in sync with the application, so you don't run into situations where the application starts and then certain assumptions about tables or columns aren't met and it doesn't work. So I think here again the message is use the simplest database migration tool that could possibly work. I do not want to influence your choice as to which one to pick, but just use one that works for you. Now, what about the logs? We talked about it. It's not 2006 anymore. The days of having logs stored on individual machines and having multiple windows with ~f and some grep expressions really belong to the past. We instead now have fantastic solutions available in the form of centralized log service where we can ship the logs. Our networks are so fast that very often we don't even need to buffer them on disk. We can send them directly to that central location. It means that we don't need to give access, even read access to anybody to those production machines because the logs are being shipped out. And they're all in one place, so you don't need to be hunting on individual machines to see where a request may have landed behind the load balancer. They're being stored and backed, so you don't run into problems in terms of, for example, auto-scaling, where certain machines may be added, but also taken away at any time, and whatever's on those machines disappears, including your log files. And you've got nice web UIs where you can search them, you can define alerts on them, you can have machines also sift through them, so you've got a whole bunch of interesting possibilities. So regardless of what you're doing, I think this is a very low-hanging fruit and a fantastic thing to go for. And you've got, again, you can build your own with Elasticsearch, Logstash, Kibana. You can buy things like Splunk. You've got great hosted services like Loggly, Log Entries, Papertrail, or CloudWatch Logs on AWS. You've got a whole bunch of possibilities. Loggly, for example, even gives you an XML snippet that you can copy-paste into your logback.xml. You stop your application, start it again, and it starts sending the logs to the cloud. So very, very, very easy to get going with. Now sessions on another interesting one. So what is at its base? What is a session? A session is really a way to identify you on a specific machine. That is really what it is about. It is not a general purpose cache. It is not just a big garbage bin where you throw a whole bunch of things in. It is really something to identify who you are on a specific machine. In the JVM world, over the last 15 years, we've had a surprisingly large number of bad ideas into how to solve this. So we first had it, of course, only on a single machine where we had some kind of cookie in the client with some session ID, and then that was basically just some kind of pointer at some data structure in memory in our server where we could then extract the information from. But then we realized, well, you know what, just one machine maybe not that great for a production system. We actually want to keep the service up if one machine dies, so we need multiple machines, so we're going to start clustering them. So we then, well, how is that going to work with the sessions? Okay, we should replicate them, so we start sending the session data back and forth, but once we grow beyond a few more machines, it's a lot of chatter on the network, it consumes a lot of RAM, all these sessions from everywhere on every machine, so we looked at things like peer election, with having just two machines replicate amongst each other, and then using techniques like sticky sessions and server affinity and session draining on the load balancer, so that the load balancer would remember which backend server has actually served which user, and then always send the request there. But the problem is that doesn't really fit in a world with continuous delivery. If somebody gets in the office in Minsk at 8 or 9 in the morning, and that person works the whole day, then that session could survive 8, 9, 10 hours. So it's much too slow to have that kind of update cycle. So instead, we should look at what other platforms have been doing. What Rails has done since version 2.0, what ASP.NET has done since the beginning, or even the Play framework on the JVM. We put the entire session in the cookie. And we can do it securely by first signing it and then encrypting it, so we can make sure that it's not being read and it's not being tampered with. And this opens up a whole bunch of possibilities. You can get rid of those annoying session timeouts where you've written your complaint letter for 30 minutes and 5 seconds, and you press submit, and then bam, session expired, sorry. Why do we have those things? Well, because we have a finite amount of RAM, and then we work on some kind of algorithm to evict the older sessions to avoid running out of resources. But with a model like this, you've delegated the storage of all those sessions to the individual clients, so that on your server, you only need to have enough memory for the requests that are being actively processed. And that's a lot less. So you can do a lot more with the same machine or work with smaller machines to serve the same amount of users. And you can get rid of annoying things like session timeouts. You can get rid of all the complexity with clustering and replication, because now you're just farming your machines. So you don't need to think about sticky sessions and server affinity, which, by the way, don't work at all in an auto-scaling world. So you get rid of all these issues, and you have a much nicer model to work with. There's a bunch of solutions available for this. There's a filter available on GitHub. Just kind of Google Java stateless session, and that's a servlet filter that you place between your application and the client, and it does all this transparently for you with no change in your application code. Now, rolling out new versions. How does that work? We've seen it briefly in the demo. We've got our version 1 of our application. We've got a load balancer sending a request to it, forward it to the application, get some data from the database. Our application is, our instance is running in something called an availability zone, just a cloud term for one or more data centers in the same location. And if you want to survive disasters, you want to run that across availability zones, in multiple availability zones. They're usually on different sides of a major city. They'll be connected to different power networks and in different flooding areas and all that, so that in case of disaster, it's very unlikely that both would go down at the same time. Our logs go to a centralized NOC server or session in the cookie. So what do we do? The first thing that we do is acknowledge that we live in a world of abundance, and we expand our infrastructure footprint. So if we have 10 instances for version 1, we start 10 more for version 2. And then we make sure they're healthy, and if they're healthy, we start sending traffic to them, cutting off traffic from version 1, and decommissioning version 1. And we've smoothly transitioned from version 1 to version 2. So what was the extra cost for this? If these would have been 10 T2 macros on AWS, for example, and we would have launched 10 more and then shut the old ones down, our additional cost for that 1 hour would have been 10 cents of a euro. That's it. So it is amazingly cheap to do things this way. But of course, let's talk about the elephant in the room. What about containers? What about OS-level virtualization? What about the Dockers of this world? How do they fit in a model like this? To be able to answer that question, we first must take a step back and look at how modern CPUs work. Every CPU shipped on the market in the last 10 years, since 2006, by Intel and AMD, has had hardware support for virtualization. This has brought two things. First, isolation of individual guest operating systems running on that CPU. The other one is a performance penalty. There's been a cost associated with entering and leaving VMs. So every subsequent generation of CPUs has worked at reducing that cost by adding additional instructions for networking, for I/O, for all kinds of things to reduce it. They've worked on optimizing existing instructions. And to the point where today, on Xen and KVM, it's within 2 to 5% of native, but the difference is still there. Now, if you run on-prem, if you've got a VM, you will have your hardware, your hypervisor, your isolated images on top, versus if you have containers, you then have your hardware, a base operating system, a container runtime, and then you've got your different images running there with no hardware isolation in between. But that's fine too, because you're not within a hostile environment, and you don't have competitors or that will try to Troyanize you there, so that's okay too. So the big question in terms of which ones to choose here is really what kind of workload do we have? Is it heterogeneous? Do you need different operating systems? Do you have stuff on Windows? Do you need things like live migration, which is still better solved at the VM level? Do you have existing investments in certain licenses of things, and maybe VMs may be the better choice? If, on the other hand, you can say, no, actually everything can run on the same version of the Linux kernel and we're fine with that, then I think containers are a great choice also. You don't need to pay the performance penalty of the isolation of the VMs. You've got a nice, simple thing. So I think there, at the end of the day, it's all your responsibility anyway. You've got to manage it all, from the data center all the way to the software. So it's all your responsibility. In the cloud, on the other hand, regardless of the model you choose, you always have the hardware and some hypervisor, whether it's Xen, KVM, Hyper-V, depending on the cloud provider you have. And with your credit card, you actually buy quite a bit more. When you buy an instance, you actually get a whole bunch of services included. You get a machine image repository. We didn't need to set up or configure anything for our AMIs. It's there. We don't need to worry about scheduling on physical hosts. They offer that solution. They'll talk to Michael ahead of time to plan for capacity. We don't need to go shopping. They'll deal with storage. They'll have a great software-defined networking solution across hosts. You don't need to worry about that. And you run your instances directly on top of that. If, on the other hand, you bring containers into the mix, you introduce a new intermediate layer where you then have your base operating system, the container runtimes, and then those images running in there. And all the services that you've been using before, you now have to solve again at the container level. Whether you use hosted services or you build your own, that's for you to decide. But the fact is, you actually have to solve all these problems twice now. Okay, so when does that make sense? To take on that responsibility for that whole other layer there running within your instances? When should you want to do that? I think let's talk economics again. We've mentioned the word business a few times. So what does €5 buy you? €5 buys you more than 1 month of T2 Nano capacity, the smallest instance running on AWS, 512 megs of RAM, 1 virtual CPU, running 24/7. So this is actually about 40 days if you calculate it exactly. Or if you translate it even smaller, it's about half a cent of a euro per hour, or about the price of 2 beers in the bar here in Minsk. And that gets you about a full month of T2 Nano. Now, so the question really is, if that's the smallest unit of granularity you're going to be working with, half a cent per hour, is that something your organization can afford as a granularity unit? If the answer is yes, then you should ask yourself, do you really want to spend the time dealing with all that? Do you want to spend the engineering effort setting it up, maintaining it, patching it over time? Or could you just get rid of it? If the answer is no, then it may be worth it to invest in that direction. You have to factor in the time that you'll need, of course, to do it, but it may be worth it to invest in that direction. At the end of the day, what really matters is that you shouldn't really worry if this machine has 200 megs of unused RAM or that CPU has got some cycles to spare. Who cares about that? Optimize for the total bill that you get presented at the end of the month. That's really what matters. And don't forget about the time of the developers and the sysadmins as well. So if we summarize and bring all that together, we've taken all the principles that we've learned to appreciate for our artifacts, where we produce one immutable unit that we regenerate after every change and promote unchanged from environment to environment to avoid the classic mistake of having a separate artifact per environment, where we have a different artifact in production than with the one we tested in test. And we've applied that for the remaining layers of our stack. To make it practical, you have to go minimal with your images, make them as small as possible. And I think a major driver into how we design our systems in the next few years will be cost. So I think this is definitely, it's early days, but this will be a big one to watch. So if what I talked about today resonated with you, feel free to go and run with it. If, on the other hand, you are running on AWS with JVM, Node, or Go, and found it interesting, I would like to invite you as well to check out the work that we're doing in that space. It may be interesting for you as well with box views. Otherwise, I would say this should have been my last slide, but I have another one for you. Thank you very much.